When I was little, I dreamed of building the ultimate medicine machine, which could figure out everything that was wrong with you and fix you all in one go, sort of like those machines that you see in the movies. And while that's definitely not possible yet, we are working on small parts of medical physics which can help people struggling with all kinds of conditions. I became interested in optics because it has potential as an imaging tool, but without any of the damaging properties of X-ray or ultrasound. It can also be used while people are undertaking normal daily activities, removing some of the stress and anxiety from the diagnosis process. Studying physics gave me all the knowledge I needed to tackle the project of creating a medical imaging machine, starting from the underlying maths, the physical construction, through to testing the device in humans, and then making improvements based on new data. My research uses near-infrared spectroscopy to generate 3D images of brain activity. The basic principle of near-infrared spectroscopy is that light shines on the scalp and travels through the skull and into the brain. This light is scattered by the tissues within the head, and some is absorbed by special molecules which we call chromophores, resulting in a small amount of light that can be detected by the optical sensors at the scalp. The modified Beer-Lambert law is used to convert the changes in measured light intensity, delta A, to the changes in concentration of these chromophores, delta X. This can be done using the relative extinction coefficient, epsilon, and the length of the path that the light has travelled. The path length is defined as the distance between the optical source and detector multiplied by the differential path length factor, which takes into account multiple scattering of the light. My job is to determine which wavelengths in the near-infrared range can do this the best, and then design custom imaging caps to test this in humans. Each hexagon on this imaging cap contains one 5-wavelength LED and 4 photodiode detectors. And hexagons are the shape that works best for this, as they can fit together on a spherical surface such as the head, and they tessellate in the way that the patches on a football do. When we listen to music, this device can see the effect that this has on brain activity and compare it to brain activity when there is silence. And this is one of the many ways that we can determine if the cap works in the way that we want it to. The other involves creating a fake brain or phantom and then seeing what happens when we add and remove oxygen. This technology could be used to help diagnose babies with brain injuries from the birthing process, or even provide an earlier diagnosis from dementia. And this is just the tip of the iceberg of the kind of research that's being done at the Cavendish that could help improve people's lives for the better.